Good morning.
Good morning.
So last class we are seeing the multiplication of two fixed point sine magnitude data, right? So the algorithm that we have seen is this is the algorithm, right? Multiplicand is in B, multiplier is in Q. A initially will be 0 and sequence counter which is equal to n minus 1. Because number of bits in the multiplicand register, multiplier register will be the sequence counter, right? Q register holds only the magnitude portion. We'll be having one more extra bit that holds the sign component. So hence, for an n bit number, we'll be having magnitude portion only n minus 1. Okay, that's why sequence counter is n minus 1. We need to inspect the least significant bit every time. If that is 0, you no need to do anything. Just shift the accumulator and Q register. If it is 1, then you have to add the multiplicand to the accumulator and then you need to shift. Okay, this procedure have to be repeated till sequence counter becomes 0. Once it is 0, you will be having the final product in A and Q register, right? So this is the multiplication operation for two sign magnitude data. Okay, and this is the hardware required. A register, B register, AS and BS holds the sign component, and QS is the sign of the resultant. A register also used for storing the sign of the resultant, magnitude of the resultant, and AS holds the sign of the resultant product. Okay, and E holds any extra carry that we are getting after adding the multiplicand to the partial product which is accumulated in A register, right? So we'll do one example on this. So I'll example on multiplication. Sign magnitude data. So the example that we have seen is this. So we'll do the same 23 into 19. 23 is 10111 multiplicand, 19 is 10011, right? So first number is 23, which is nothing but 10111, which is the multiplicand. And next number is 19, which is 10011. It is multiplier, right? Let us suppose our numbers are plus 23 and minus 19. Okay, so plus 23 means positive, so sign component is 0. Minus 19 negative, so sign bit is 1, right? Okay, since the data represented in sign magnitude data, this is how we have to convert it into binary. Okay, am I clear?
Yes, ma'am.
Okay, so here one thing I want to tell you. Let us suppose my register is able to store 8-bit number. Okay, and I have plus 23. How this is stored in my 8-bit number? Because it is having just 1, 2, 3, 4, 5, 6 bits. Okay, but my register should able to store 8 bits. What about the remaining bits, remaining 2 bits? How they are stored? Can anybody tell me how plus 20
2 zeros.
8-bit number? Yes.
2 zeros in the front.
2 zeros are added in front.
Zeros will be added at the left side of the number. 0, 0, 0, 1, 0, 1, 1, 1. Okay. Similarly, how minus 19 is stored?
1 1.
1,
100 100 11.
Yes. 100 100 11. This is correct. Okay. Because the most significant bit, whatever it is there in the register, that has to represent the sign component. Since it is minus 19, that will be 1. And the remaining bits will participate in the magnitude, right? So we should not change the magnitude. Only for the magnitude portion, this will be, the remaining 2 bits will be 0. Okay. So this is for 8-bit extension, right? Similarly, if I want to store it into 16-bit register, how it will be? The remaining extra 8 bits, whichever are there, those will be zeros only.
0.
Am I right? Most significant bit is 1. Remaining bits are zeros. Okay.
Yes, ma'am.
Am I clear? Likewise, you have to represent sign magnitude data. Okay. Only the sign bit is dragged to the most significant bit position if you increase its length to 16 or 32 or any n. Remaining all bits are made 0. Okay. In positive case, it is 0. So it won't be any problem. You can extend the remaining all bits to 0. It doesn't have any issue. Okay. So this is sign magnitude data. Okay. So whenever we come for a 2's complement multiplication, then I will explain how to perform the same operation in case of 2's complement data. Okay. That's what called a sign extension. Okay. Is this clear?
Yes, ma'am.
Okay. So now let us go back to our example. So these two are the numbers that we want to perform multiplication. So 23 into minus 19, I should result minus 437. Okay, so this is what you are expecting, right? Minus 437 in binary. In binary, this one 1101 10101. 1101 10101. This is magnitude portion. I have to add sign to it. Since the signs are opposite, so I'll be having sign 1. Okay. This is what the result that you are expecting. Now we have to perform the same thing with the help of algorithm. Let us work out the algorithm. So I will insert a table. So I require a multiplicand. Multiplicand will be stored as per the algorithm. How the registers are used. See what B holds. B holds
Multiplicand.
multiplicand. Q holds multiplier.
Multiplier.
Right? Okay. A holds initially 0. Right? Sequence counter holds n minus 1. N is the number of bits in your total multiplier, right? Complementer and add, right? So as per the algorithm, you may require to perform addition, right? So you may require to perform the addition operation if the least significant bit is 1. Otherwise, you no need to perform the addition operation, right? Okay. So now
Yes, ma'am.
I require E bit A, which holds your initial accumulated product or partial product, which is 0 0 0 0, because n minus 1 is 5 in both the cases. Okay, in both the cases it is n minus 1. So one condition here, better to choose the n is same in both multiplicand and multiplier. If they are not same, extend the other bits. Okay. So let us suppose it is just 3 plus 3, then only 2 bits will be there, right? But your multiplicand is 5 bits. It is better to extend it to 3. so that your A and the Q registers both will be of same size, because in any computer, all the registers will be of same size, right? So you have to extend even the multiplier to the same size of multiplicand. If the multiplier is bigger in length, then extend the multiplicand to the same size of the multiplier, so that make sure all the registers are of same size. Okay. A is 5-bit length, okay, which is 0, and next holds your Q, which is nothing but multiplier, right? So multiplier is in Q register 10011, and we need to inspect the QN bit, least significant bit, every time. And what is B? B is the multiplicand, which is 10111. Okay. Now, as per the QN, so first significant bit is here 1, and we require one more thing for sequence counter, right? Okay. So I can take this to sequence counter. Initially, how much is the sequence counter? 5. Okay. Now here QN. What is QN? Least significant bit, that is 1. So as per the algorithm, what you have to do, if the least significant bit is 1, you have to add multiplicand to the accumulator, right? So what is B? It is 1011. Add that to your accumulator. 10111. So I'll be getting result as 10111 only, because A is already all zeros. Okay. So after adding A, we got this value, and the Q is the same value, 10011. Okay. Right. So what you have to do after addition? After addition, as per the algorithm, you have to shift right side by 1 bit. Okay. So you need to shift right side by 1 bit along with E. E is 0 as per this addition. So newly added E bit is 0, and so this is 100. After shifting, this is 0. Here we'll be getting, sorry, here we'll be getting 1, 0, 1, 1, and this least significant bit will occupy the most significant bit in Q, 1, 0, 0, 1. Am I right? And last
Yes, ma'am.
bit will be gone. Okay, it was shifted out of the register. And anyway, that we have inspected already. So we are shifting right side by EAQ. Okay, we are shifting right side. After that, you need to reduce the sequence counter by 1, so that becomes 4, and this is not at 0. So you need to repeat for the second cycle. Okay. So in second cycle, now what is the least significant bit? It is 1. So again, now the bit position is again 1. And what you have to do, you need to add B again to the accumulator. So B is 10111. So you have to add this. What is this? 1 1 is 10, right? 1 1 is 1 0, and 3 ones, 1 1, 2 ones, 1 0, again 2 ones, 1 0, and again 2 ones. You'll be having E as 1, and this is 0. Okay. So what is the result? 0 0 0 1 0 is after adding B to the partial product available in A, and your E is 1. Am I right? Is that clear?
Yes, ma'am.
Okay. So this is the result of addition. Okay, Q is same. There is no change in Q. After adding addition, after adding B to A, then you have to do again right shift. Okay, so after right shifting, newly added bit in E is always 0, and this 1 will be come into most significant bit of A. 0, 0, 0, 1, and the 0 is placed in Q most significant bit 0, 1, 1, 0, 0, and the inspected bit 1 will be lost. And then now sequence counter is reduced again by 3, and it is not at 0, so you have to repeat for second cycle, third cycle. Am I clear?
Yes, ma'am.
Now what is the last significant bit? 0. So since Qn is 0, what do you have to do? You
Right
need
shift.
to add multiplicand to the partial product, because the inspected bit is 0. 0 multiplied by multiplicand is nothing but 0, right? So you no need to perform addition. Okay, we will do only whatever it is there in A, those are as it is. This addition operation is skipped, but right shifting has to be performed. Okay, so after right shifting, this will be 0, again 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, and reduce the sequence counter by 2. Since it is also not at 0, so again inspect the second. Now my Qn is 0 here, so this bit, it is 0, so hence you don't require to add again. Whatever are there here, those will be resulted as it is. There is no addition, but there will be right shift. So you have to do right shift. 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1. And then sequence counter is reduced by 1. Okay, not at 0. So again, inspect the most significant, least significant bit. Since it is 1, so you have to perform addition. Okay, so you have to add B. B is 1, 0, 1, 1, 1. Okay, so perform the addition. What is the result? So it is 1, 1. This is 1, 0, 1, 1. Okay, there is no carry. 0, and this is 1, 1, 0, 1, 1. Am I right?
Yes, ma'am.
Okay. And Q is same as it is. It is 0, 1, 0, 1, 1. Okay. Now right shift. It is 0, 0, 1, 1, 0, 1. And this 1, 0, 1, 0, 1. 1 will be lost. And sequence counter becomes 0. As and when SC becomes 0, the algorithm is finished. Right? So now your result is in A and Q register. So result A Q register, which is nothing but 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. Okay. So the number of bits here. This forms the magnitude, right? And sign, according to the sign, AS is equal to plus 23. So AS is 0. Sorry, QS is 0. BS is so what is B holds? B holds multiplicand, right? So BS we have to talk about. AS is equal to BS XOR operation with QS, right? BS holds the multiplicand, whose sign is positive, and QS holds the multiplier whose sign is negative. So hence 0 and 1 is the result. Okay, sign component. So total result is including the sign. So the product is minus magnitude 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. Okay. So if you check, this will be minus 437. Am I right? So these are the bits. We have extended it by 1 bit with the 0. That doesn't matter. Okay. These are the magnitudes. Am I correct?
Yes, ma'am.
So this is how you have to explain the algorithm sign magnitude data with an example. Okay, whatever it is the data that they have given, you need to show everything. Okay, as per the flow chart you have to follow. Is there any doubts in this algorithm? You want me to explain another example or else shall we move to next topic?
Next topic, ma'am.
Okay. Anybody please respond. I'm getting response from only one person. You have to interact, ma. If you have any doubts, you can interrupt me. Okay. Then we move to next topic. The algorithm now. Multiplication algorithm on sign 2's complement data. Okay. So let us do 2's complement data. So before going to this algorithm, the 2's complement data representation means if your number is positive, then there won't be any change in representing the number. If the number is negative, then its corresponding 2's complement value is stored in your registers. That's what the 2's complement representation, right? See, for example, consider a number 14 plus 14. Okay, how it is represented? Plus 14. Can you tell me the number in binary?
110. 1110.
1110. Is it positive or negative?
It's negative.
But I asked you to tell plus 14.
We have to add 0 to the most significant.
0, 1, 1, 1, 0. Yes, plus 14. Okay. See, universal notation, most significant bit 0 means the number is positive, otherwise it is negative. Okay. Right. In any case, number, if it is positive, then you should make sure that the most significant bit is 0. Okay. This is plus 14. Okay. So here, any number, which obviously it is a combination of zeros and ones, right? If any number have a sequence of ones and zeros, a series of ones in it, okay, right? Any number, if it is having series of ones, which should end with 0, right? With start from 2 power m2 2 power k. In any number, if it is having series of ones, start from 2 power m2 2 power k. Okay, because you have to apply powers of 2 to get the magnitude, right? So this is 2 power 0 and 2 power 1, 2 power 2, 2 power 3 and 2 power 4. Okay, right? So if any number is having series of ones start from 2 power m to 2 power k, then that number can be represented as that number x is equal to the value 2 power k plus 1 minus 2 power m. Okay. Any number, if it is having series of ones, start from 2 power m to 2 power k, where your m or k is greater than m. Okay, or else m less than k. Okay, so in this situation, your number can be represented like this. See, for the same here example, here what is the value of m? What is the value of m in our example? Plus
Okay.
14. M is
3.
1. K is 3. Okay.
3.
M is 1, K is 3. So your number is 2 power 4. 2 power K plus 1, right? So 2 power 4 is nothing but 60 minus 2 power 1, 2. 16 minus 2, 14. Am I right? So 2 power m plus K plus 1 minus 2 power m, which is 1. So 16 minus 2, which is equal to 14. And that too, it is plus 14. Okay. So any number here which is having series of ones, start from 2 power m to 2 power k, then that number can be represented as powers of 2, as 2 power k plus 1 minus 2 power m. Okay. So when this number is multiplied by some other number, okay, so then what is the product result? The multiplicand has to be, this multiplicand has to be shifted left side by m number of bits, right? So whenever a number is shifted left side by 1 bit, it means it is just nothing but multiplying by 2. Am I right? Shifting left side is nothing but multiplying by 2. Shifting right side is nothing but dividing by 2. Am I clear? Is that
Yes, ma'am.
okay? So the multiplicand has to be shifted left side by m bits, and that value has to be subtracted from another product where the multiplicand again shifted left side by k plus 1 bits. Okay. So in this way, this is what the procedure that is followed in Booth's algorithm. Okay. So the algorithm that multiplies the sine 2's complement data, it has a specific name, that is what called Booth's algorithm. Okay. Before going to the algorithm, let us see this principle with 1 or 2 examples. Okay. So take any number, check both positives and negatives, negative numbers. Let us take a number minus 19 that we have seen earlier. Minus 19. How a number is represented in minus 19? Okay. Binary, corresponding binary value. Your 19 is this much, right? 10011. Plus 19 is 0, 1, 0, 0, 1, 1. This is plus 19.
Yes, ma'am.
So I want minus 19, so I have to take 2's complement of it. So first to take 1's complement, I will be having 1, 0, 1, 1, 0, 0. To this you have to add 1. So I'll be getting 1, 0, 1, 1, 0, 1. This is what? Minus 19. Okay. So how can you represent this as per this notation? So how can you represent this minus 19? So it is having series of ones and zeros, that is sure. By applying powers of 2, here it is 2 power 0, and this is 2 power 1, this is 2 power 2, and this is 2 power 3, this is 2 power 4, and this is 2 power 5. Okay. So here there are several series. Okay, it is not just one, it is accumulated with them. Okay, we will be having, see here a set of ones, here a set of ones, and here set of ones. Okay, so you'll be having three different such terms. Okay, so in this case, right? So this is my m, which is equal to 0, and it has a series of ones start from 0 to end. Where it is ended? What is the value of k for this series? K is also 0. It is ended that itself. Okay. I have a series of 1 here, only 1 I have. So my m is 0 and k is also 0 in this case. And in the second case here, my m is equal to 2. And what about k? K is 3. My k is equal to 3. Excuse me, ఒక్క నిమిషం. Hey, shit. Sorry, Amma. Sorry for this. So, where are we? Okay. So here my m is equal to 2 and k is 3. Okay. K is 3. And in the last case, my m is equal to 5. And what about k?
5.
No, it is not 5 because, excuse me. Okay. See here, if it is end with zeros, then only k value will be taken. Okay. Since it is not end with 0, then there is no value for k. There won't be k term in this value. Okay. So by taking this, first term, we will come in this way. There is no k term. So this will not be there. It starts from minus 2 power m is equal to 5. So minus 2 power 5 plus next term k3 m2. So 2 power k plus 1. So 2 power 3 plus 1, which is nothing but 4, minus m is 2 square, plus next series of ones, m is 0, k is 0. So 2 power k plus 1. So 2 power 1 minus 2 power 0. Okay. So this is 2 power 5 is minus 32 plus 16 minus 4 plus 2 minus 1. Okay. So all the positive terms we have 18, negative terms minus 37, right? 6. This is 5 and 5. Minus 37 or negative times. Positive terms are 18. 7 plus 2, 9, 2 minus 1, 1. Okay. So we'll be having minus 90, which is the result. Am I clear? This is how
Yes,
you
ma'am.
have to represent any number which was represented in 2's complement with the series of 2 power k plus 1 minus 2 power n. Okay, only the consideration, you can have a least significant bit as 1 without preceding it by zeros. Okay, no need of 0 at the least significant bit side. Okay, that can be treated as 1, but k should be considered only when it is end with 0 only. Okay, this is very important to be remembered, right? Otherwise the value k term won't be there everywhere. Okay, m doesn't have any issue, but k, whenever it is end with 0, then only the number is positive. So 2 power k plus 1 term will be appeared. Otherwise k term will not be there, right? So this is how the numbers can be represented in this way. Now when this number is multiplied by a multiplicand, okay, so your multiplicand now has to be shifted by 0 at the times, and it has to be subtracted, and the same multiplicand has to be shifted by 1 time left, and it has to be added. Okay, the same multiplicand now it has to be shifted twice by 2 bits by left side, and it has to be subtracted. Okay, and 4 bits by left side, and it has to be added. 5 bits by left side, and it has to be subtracted. Then you will be getting the total product. Am I clear? Okay, so now tell me when you need to subtract, when you need to add.
For even number of shifts, we have to subtract. For odd number of shifts, we have to.
For even
No, ma'am,
number
nothing,
of
ma'am. Nothing, ma'am.
You can't say the even number or odd number of shifts. See, here it is 5, here it is 2. This is odd, this is even.
Yeah, yes, ma'am.
Okay, so this is not the case. You need to consider this series of ones. We'll be having a term, m term, that has to be subtracted. For k term, it is added, right? When the m term appears, when the k term appears, that has to be checked. Okay, so when m term appears, whenever you encounter, while we are inspecting the multiplier from right side, if you encounter the first significant, least significant bit as 1, whenever you encounter the first one, okay, right? So whether least significant bit is 1 or else there is a possible term of 1 0. Whenever you have encountered 1 0, the previous bit we assume it as 0 and the present bit is 1, then we require to subtract, right? So 1 0, this causes the term m term, and you require to subtract. The shifted multiplicand need to be subtracted from the previous product, which is obviously we'll take initially as 0, right? Whenever we have the k term, that has to be added. Okay, when we encounter k term till 2 power k, so after this you should have a 0. So whenever you have a sequence like 0 and 1, present inspected bit 0 and previously inspected bit is 1. Okay, in this case, whenever you have 0 1 term, then you have to perform addition of the multiplicand, which is of course shifted left side. That multiplicand has to be added to the product, partial product, which is accumulated in somewhere, some register. Am I clear? And if both are ones, if I receive both are ones or both are zeros, okay, both ones are both zeros, is there anything that we are doing?
No, ma'am.
We were not doing anything except the shifting of left side by the multiplicand, because see here 2 power 2, since here we have a sequence of 1 1, this in this case we were not doing anything except shifting it by 1 bit left side. So that 2 power 3 will be gone. And 2 power 4 will be in the correct position again. Right? So if the present inspecting bit is 1 and the previous inspecting bit, if it is 0, okay, this is the present bit and this is the previous bit. Let us take this as q1 plus 1. Okay. If we have a term as 1 0, what you have to do? 1 0, then it leads to m term. So you have to perform subtraction operation. Okay. For 0 1 case, the present inspected bit is 0 and the previously inspected bit is 1. In this case, you have to perform addition of the multiplicand to the previous product. Add operation will result. If either 1 1 or 0 0, nothing, no operation will be done. But in all the three cases, you have to perform the shift operation of the multiplicand. Okay. So the multiplicand has to be shifted. Rather than shifting the multiplicand, the simplified step that we have taken in sign magnitude form. What is this? Rather than shifting the multiplicand by left side, what we will do? We'll shift the accumulated product by right side so that they both will be aligned, right? So we will shift the accumulated product by right side. Okay, in both the three cases, the shift operation is compulsory. The extra operation, whether it can be subtraction or it can be addition based on the sequence of present inspected bit and previously inspected bit. Okay, so this is what the Booth's algorithm. Am I clear? Which completely depending on how the number is represented. Right. So this is the key for Booth's algorithm. Is it clear? If you have any doubts in this representation, we will take 2 to 3 examples and then we move to algorithm. Is that fine, or else shall we go directly to algorithm?
Examples, ma'am.
Okay. So we will see the examples. You tell me any number that you want to represent with the help of that sequence. Any number, maybe bigger or smaller. Tell me a number.
Minus 30.
Minus 30. So decimal 30 in binary, this is what one? 0 0 0 1 1 1 1 0. Okay. So you want minus 30. So since it is negative number, it has to be represented in 2's complement form. Okay. So plus 30 is 0 0 0 1 1 1 1 0. Okay. Minus 30 you want. So take 1's complement first. 1 1 1 0 0 0 0 1 and add 1 to 8. So I'll be getting 1 1 1 0 0 0 1 0. Am I right? This
Yes,
is
ma'am.
minus 30. Now take the terms k and m. See, this is 2 power 0, 2 power 1. 2 power 2, 2 power 3, 2 power 4, 2 power 5. 2 power 6, 2 power 7. Since there is no 0 here, okay, so it is being continuous, okay. Even if you extend this to 16-bit length, right, in 2's complement form, if you want to extend, this is a 8-bit representation, right? So if I want to save the same number minus 30 in a 16-bit register, how should I save? What is the value that can be stored in a 16-bit register? If I want to store it in 16-bit register, so what is the value? Minus 30. Ela save avutundamma 16 bits lo. We have seen how it is being increased to larger lengths in sign magnitude. The same way in 2's complement form, how the number is saved. How plus 30 is saved? For example, plus 30, there won't be any problem. Whatever are the extra bits, we'll have to add 8 more extra bits. Those are zeros only. Okay, whatever are the left side, if it is 0, since a positive number, you can extend left side by zeros, not a problem. But you want to extend it to larger length in case of a negative number. You need to start from positive number. Let us take plus 16. This you have to complement, right? 1 1 1 1 1 1 1 1 1 0 0 0 0 1, and you have to add 1. So how much we are getting? 1 1 1 1 1 1 1 1 1 1 1 0 0 0 1 0. Okay, see the difference? These are the 8 bits here. These are the 8 bits here. What happened? The extra 8 bits, those also
All ones are
All ones.
resulted all ones.
ones.
Okay, because in 2's complement form, we are complementing and doing whichever is the most significant bit in your input. Okay, that has to be copied to the all most significant bits. This is what called this procedure. We call that as sign extension. You need to perform sign extension for increasing any number to larger lengths. Okay, so whichever is the most significant bit, that has to be extended to all the other extra most significant bits. In this case, my most significant bit is 0, so I'm extending it with all zeros. But in this case, my most significant bit is 1 because my number is minus 30. Okay, so that most significant bit has to be extended to all ones. Okay, similarly, if I want to represent this to 32-bit bit, the same one has to be extended to 16 more bits. Likewise, 64 bits, anything. Okay, so whenever you complement it, all of those becomes 0. The magnitude doesn't vary. Okay, right? So as we are extending this to further, there won't be a limit for k here. So hence we should not consider the term k unless until it is ended with 0. Am I clear?
Yes, ma'am.
Yes, ma'am.
Okay. So now we, in this case, for 8-bit only, if I consider this is 2 power 1 and your m start with 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. This is 2 power 5. Okay. And 2 power 6, 2 power 7. Likewise, it may extend. So there is no where we can observe present significant bit as 0. Present inspected bit will not come 0 at any case. So hence we won't consider the k term. Okay. So by considering this, this here my m is equal to 5, but there is no k. And here my m is equal to 1 and k is also 1. Okay. Since I have received a 0 here. Now by combining, there is no k, so additive term will not be there. There is m, so negative term, subtractive term is 2 power m, which is nothing but 5. Plus, there is k, so additive term is 2 power k plus 1, 1 plus 1, which is nothing but 2. Subtractive term minus 2 power m, which is nothing but 1. Okay, minus 2 power 5 is 32 plus 2 power 2 is 4 minus 1. Minus 33 plus 4.
Minus 2.
Sorry. 2 power 1 is 2. So minus 34 plus 4, which is equal to minus 30. Okay. Is this clear?
Yes, ma'am.
Yes, ma'am.
Do you need another example or else algorithm? We have left with 5 minutes.
Algorithm.
Shall we proceed to algorithm?
Yes, ma'am.
Okay. So this is the name is Booth's algorithm. Other name which performs the multiplication on 2's complementary data, that algorithm is called Booth's algorithm. Okay, only specific name they have given as per the designer. Booth algorithm gives procedure for multiplying binary integers in 2's complement representation. So a 2's complement number can be represented as a string of ones in the number from bit weight to power k to bit weight to power m, where k is greater than m. Okay, k is greater than m. That can be treated as 2 power k plus 1 minus 2 power m. So example that we have seen already, plus 14. So here I have a series of ones from 2 power m where m is equal to 1 to 2 power 3 where k is equal to 3. In that case, I can represent like this: 2 power 4 minus 2 power 1. Okay. And for such a number, if it is one of the number to perform the multiplication and m is the multiplicand, whenever we want to perform like m into 14, I know my 14 can be represented in this way. Then my multiplicand has to be multiplied by 2 power 4 minus m into 2 power 1 will be your final product. Okay. So this product can be obtained as simple as shifting the multiplicand by 1 bit, because the power of 2 is 1 bit left side, and shifting the multiplicand by 4 bit left side, I'll be getting these two different terms and perform this operation plus and minus, then I'll be getting the total product. Okay. So this is the simple procedure that we are following. Okay. So to do so, the simplifications in our algorithm is, we know whenever when the negative terms is coming, whenever you have encountered 1-0 series, present bit should be 1, previous bit should be 0, or else first bit itself it can be 1. Okay. So 1-0 series, or else first bit itself is 1, assuming that the previous bit was 0. Okay. In that case, the negative term will come. 0-1 case, the additive term, positive term will come. And if both the bits are same, there is no operation is performed on the multiplicand except shifting. Okay. So even in here shifting, rather than shifting the multiplicand left side, we will be shifting the product by right side. That is the same procedure that we are following even in 2's sign magnitude data. Okay. So as in all multiplication schemes, Booth algorithm requires examination of the multiplier bits and shifting the partial product. So prior to shifting, the multiplicand may be added to the partial product or subtracted from the partial product or left unchanged according to the following rules. The multiplicand is subtracted from the partial product upon encountering the first least significant bit 1 in a string of ones. Whenever you encounter a first 1 in a string of ones, in that case the multiplier is subtracted from the partial product. The multiplicand is added to the partial product upon encountering the first 0, provided that there was a previous 1 in the string of zeros. Okay. Right. So first 0 encounter avali, provided that there should be a previous 1. And the series should be 0-1. Ilane undali. Okay. So but there won't be a condition for m. First 1 eppudu encounter aithe, that will be considered as m. But k term only 0 should be appear, provided previous bit should be 1. 0-1 compulsory undali. Okay. Then multiplicand is added, and the partial product will not be changed whenever the multiplier bit is identical to the previous multiplier bit. Either it is both zeros or both 1, the partial product will not be changed. Okay. After performing this, the partial product is shifted right side. Rather than shifting the multiplicand by left side, we will shift the partial product by right side. Okay. So this is the simple algorithm, Booth's multiplication algorithm. Coming to the hardware, so we'll be having 2 registers, BR register which holds the multiplicand, QR register, this holds the multiplier, and A holds the partial product. Since there are no flag bits, one bit registers which holds the sign, because in 2's complement data, sign and magnitude are not separated. Sign bit is also treated as if like magnitude bit, and we perform the operation. Okay, right? So BR register holds the total n bits of the multiplicand, and the QR register holds the total n bits of the multiplier. So the sequence counter will be the n. Here SC is n, number of bits in the multiplier. Okay, and first least significant bit will be in Qn. The previous shifted out bit will be in Qn plus 1, because whatever is the shifted out, that also be inspected for performing either addition or subtraction or no change. Okay, so that's why we are storing one more bit register which holds the shifted out bit. Okay, so initially Qn plus 1 will be 0. So if as and when Qn is 1, then I will perform subtraction, because encountering first 1 will perform the subtraction, just assuming Qn plus 1 as 0. Okay, right? So subtraction nothing but in AC minus BR you have to do. So minus BR, how can I do? Rather than going by parallel subtractor, I will use the same parallel adder, but BR will be complemented and given. Okay, so BR will be 2's complemented, and it gives for the parallel adder for addition. Okay, so subtraction is here is executed by 2's complement addition. Okay, after adding the extra bit, if you get any extra bit, that will be saved in E bit. Okay, likewise, if you get a sequence of 0 and 1, then it will be added and then shifted right side. Okay, right side always it is shifted till the sequence counter becomes 0. So this is the flow chart. Multiplicand is in BR register, multiplier is in Q register. Your accumulator initially 0. Qn plus 1 is also forced to 0 initially, and SC is equal to n, total number of bits in multiplier, including the sign. This is not n minus 1. Okay, Qn and Qn minus 1 need to be inspected. If it is 1, 0, first 1, it leads to subtractive term, m term. So subtraction is performed. AC minus BR is done by 2's complementing and then adding to AC. Okay, addition is performed like this, AC plus BR, and we'll be getting after doing this, if both are same, no operation is performed. After doing that, we will shift the right side A and Q register, not just simply shifting. The shifting here is arithmetic shift right, because most significant bit of accumulator holds the sign that has to be treated properly. If the sign bit is 1, then newly added extra bit should also be 1. Newly added most significant bit should be 1, keeping the value of the number same. Okay, see, a negative number should be a negative number even after shifting. For that, we will go by arithmetic shift rather than simply logical shift. Okay, right? If the most significant bit of A is 1, then newly added extra MSB bit for performing the shift operation right side is 1. Otherwise, it is 0. After that, sequence counter is reduced by 1, and then the procedure is continued. Okay, so till the end. Right? Are you clear with the difference between arithmetic shift and logical shift? Do you have any idea?
Yes, ma'am.
Yes. Any idea on this shift operation, arithmetic and logical shift? If you don't have, then we'll repeat the shift and then we proceed the example of the algorithm. Okay. So you please refer and kindly ask me if you have any doubts. Let me take the attendance meanwhile. For 65 absent. 67 absent, 72 absent, 82 absent, 93 absent, 97 absent, 100 absent, 110 absent, 113, 114, 115, 120 absent. 7, 8, 9, 10, 11, 12. Okay. So absentees are 65, 67, 72, 82, 93, 97, 100, 110, 113, 114, 115, 120. 12 absentees. Okay, ma'am. So, any doubts? Okay.
No, ma'am.
Okay. Bye. Bye for today. Thank you.